Hello and welcome to the Introduction to Limits. In this video, we'll be talking about what exactly limits are, their notation, and how to solve them throughout. Yes. And we're finally done with all the tiny little things that we need to know in order to get to this step. So let's get started and talk about how we would write out a limit. But first, let's talk about the difference between a function versus a limit. This is really important to understand. A function, we would express it by writing maybe f of x or g of x or h of x, whatever, and we would put of x inside to note that we are putting some function with our input value of x, and then we write out our expression. So f of x is equal to, for example, x squared plus 3x plus 10, or plus 10, yes. And then we go about solving this once we're given the value that we need to plug in to x. So if we see something like this f of 3, we know that 3 must be substituted for all the x's, and we can compute that value. So when we plug it in, we get 3 squared plus 3 times 3 plus 10, which gives us 28. So we know that 28 is the value of the function when x is equal to 3. But what do we know about the limit? So let's talk about what the differences are between a limit and a function. A function can have no discontinuities when you're trying to solve for it. If it does have a discontinuity, it's considered undefined or does not exist, and we move on with that because there is no value there. But when it comes to limits, that's not the case. Even though there is a discontinuity, we're trying to find the value that it's approaching. So what value are we close to? So let's start off by writing out the proper notation of a limit. We express limits by using a cursive L followed by IM, which stands for limit. So limit of a function as x approaches a number. So a, f of x maybe, is our function. So a is our number in this case. Let's start off, to make it easier, let's actually use some sort of function to put in there so I can show you how to solve it. First, we write out our limit notation, limit as x approaches 3 maybe, and we'll use the same function that we did just now when we were solving for 3. So x squared plus 3x plus 10, right? And we want to know what that is equal to. Now, the first step in this type of problem is to plug in. First step is to always plug in the value that we are given. And in this case, we're given 3. We're trying to find as x approaches 3. And we can just simply plug it into the equation and get a value out of it. So if I were to plug it in, 3 squared plus 3 times 3 plus 10, and you get 28. So since we have a value and it is defined at that location, the limit and the value of the function are equal, and you have 28. So that's really important. It's really important to consider. When a function is continuous, the limit of the function as it approaches a value, so a of f of x, is equal to f of that number. So f of a in this case is just the notation that I'm using with no specific value. But in the case of what we just did here, our limit as x approaches 3 of x squared plus 3x plus 10 is equal to f of 3. So we know that they're equal. But what if the function is not continuous? What if there is a discontinuity, like we've mentioned in our previous video talking about jump discontinuity, our whole, or some sort of asymptotic behavior, or something else that we can't actually know the value for? So let's take the example of x squared plus 10x over x. We know that in this case, there is a discontinuity here at 0, because if we plug in 0, we would get 0 over 0, and that's not a number. Try plugging that into your calculator and you would automatically get an error. So that's important to note that there is a discontinuity there. So let's find the limit though. So limit as x approaches 0 of x squared plus 10x over x, and we're trying to find the value to that. Like I said, the first step is always plug in. So let's plug in 0 to this equation. Plugging it into the equation yields us 0 squared plus 10 times 0 over 0. So we know that it basically equals 0 over 0. So we're done, right? That's our final value. There is nothing there. It doesn't exist. Wrong. When we're looking at the limit, we're trying to find what value it is approaching, not the exact value there. So we're not actually done, and we can't equate the two. So we need to change our notation. It's not equal to 0 over 0. It yields us 0 over 0 when we plug in. And it's really important to use a different notation like this, like the one that I'm showing you here, instead of saying equals to 0 over 0 when you're showing your work, because you can actually get docked for that by some professors, or if you're taking an AP course, that will yield you points off. So make sure you change your notation there and you don't set it equal to. That's really important. And 0 over 0, what we call in calculus, we call this an indeterminate value. Because it is undefined. But we can continue this problem, and we can continue to solve it by going on to step 2. Step 2 is factor. So now that we have decided that it yields us an indeterminate value, we can go ahead and factor out our f of x. Now, I'm going to continue, say limit as x approaches 0. This is really important that you continue to write limit, because you are not looking for the value, you're looking for the limit. Remember that. Okay, and then you can pull out the x, because we know that that is a common term in the numerator. So x squared, now that becomes x plus 10, which was previously 10x. All of that over x, right? And now trying to solve for that, but we can immediately eliminate our two x's, right? We divide them out, and we get limit as x approaches 0, and our function is x plus 10. Note, once again, this is really important. This is why I'm stressing this. The limit and the function are not the same, once again. And if you were to write this out, and if you were to actually factor out this equation in reality, you would get the same thing. You would get x plus 10, but you would have to tag it with, so your function would be f of x equals x plus 10. You would have to tag it with x cannot equal 0. This is to show that there is some sort of undefined behavior at that point, and that's where you have your hole when you're back in geometry or back in algebra 1, where we would express that hole and then continue our graph. So this is similar to that, but you have to make sure to note that if you're dealing with regular functions. But in this case, since we're dealing with limits, we don't have to acknowledge that. We just have to acknowledge what value it's approaching. So plugging in 0 into this equation, so our last step, we need to plug in to our simplified equation. So once we plug into our simplified equation, we get 10. Now I've already pulled up a graphing calculator with this equation put into it. So I'm going to pull that up real quick. Okay, as you can see over here, I have a graphing calculator pulled up, and we're looking at the value at 0, and we have that value, as you can see here. And this is the axis that's supposed to represent that. And when I get closer and closer to 0, it is approaching 10. But when I hit exactly 0, we get undefined. like I showed you the whole behavior. But after you pass 0, you are getting values higher than 10, and before that, you're getting values closer to 10. So your limit is 10 because the function is approaching 10.